This video covers a review of Chapter 4, Alkanes and Cycloalkanes. Alkanes and cycloalkanes come in all forms. I've highlighted here just a few constitutional isomers of C6H14. Remember your rules about degrees of unsaturation. Actually, this one is C6H12, so it's not a constitutional isomer, but the other ones are. When we have no degrees of unsaturation, then the number of hydrogens is equal to 2n plus 2, where n is the number of carbon atoms. Review table 4.1 for nomenclature of alkanes and cycloalkanes. You can disregard the naming of bicyclic compounds. The main two parts of Chapter 4 are Newman projections and projections of cyclohexane. With Newman projections, what we need to appreciate is the perspective that we are looking at a compound from one direction. So we want to have our eye pointed toward a bond angle. Let me put a blue mark over the carbon in the front and a red mark over the carbon in the back, so you can see in the structure on the right an attempt to illustrate that perspective. Notice that you've got your up hydrogen still going up, and then the one going down to the left is down here, and finally the one coming out forward is here. And in the back we have these in a conformation where the hydrogens are not eclipsed from each other, so we're avoiding eclipsing. In the back we have the intersection of three lines is one of the carbon atoms, and then the carbon atom that is behind us is this entire circle. So all of the circle behind us is representing the carbon atom in red. This is our lowest energy conformation. Next, if we look at the molecule butane, we can consider that there are different lower energy conformations, and they're not all the same as each other. In the first one, where we'll call this conformation A, we have the two methyl groups opposite to each other by 180 degrees. If we rotate this molecule, then in the second conformation, B, we have them quite close to each other, and the same is true for conformation C, which needs another methyl group there. When you rotate around this circle and consider the conformations that are possible, we have conformation A starting out as the lowest energy conformation, and then we rotate to B, and we have then C, which is equivalent in energy, and then we go back to A, which is again the lowest in energy. At the top of this graph, let's call it conformation D, is one in which all of the groups are eclipsed, and in particular, our largest two groups are eclipsed. This is a source of strain in these conformations to be interacting with each other, And also, cyclic systems have strain that we have to be aware of. Cyclopropane, for example, has bond angles of 60 degrees, which are quite strained. In some cases, they're called banana bonds, in case you want to Google that and read more about that subject. With cyclobutane, we have 90-degree bond angles, and we keep going up in bond angles until we get to 135 for cyclooctane. And there's something different, though, about cyclohexane with 6 carbons. That even though it has a bond angle of 120 degrees when it's written out planar, it has a unique heat of combustion in that it's the lowest heat of combustion per the methylene cyclic group. Why is that? Well, that's because it does not exist as planar. It exists in a chair conformation in which you have tetrahedral bond angles. You've had plenty of practice drawing chair conformations. If it is still hard for you, I'm going to draw just a new chair to show how I draw it. I do one zig there and then another there. It doesn't lead to the best chair necessarily, but you can keep practicing that. Some people, let me do in green another way, like to do 2 parallel lines and then have a methylene group coming up and down. That works pretty well too. If you're still having chairs, what I do is give you advice that you take a chair from your book and you just take a piece of paper on top of it and you trace the chair over and over until you get comfortable drawing it. You might even get better than me. In the chair we have 6 axial and 6 equatorial hydrogen atoms, where we've got 3 up and 3 down. So let me put our axial hydrogens in green. Notice that we've got 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. It's for every other one. Whereas the equatorial ones I'll go in and highlight in blue. And the equatorial hydrogens are like having hydrogens around an equator. So if you think of your chair as an equator, it kind of works. This is not going to be the best drawing. Maybe you can kind of see that those blues make up an equator. When you're drawing derivatives of cyclohexane, you need to be careful that you put compound substituents in the right position. For example, if you have the choice to put a substituent in the equatorial position, you should. So in this compound, methyl cyclohexane, which I noted first as a wedge, but then I took the wedge away because this is not a stereoisomer. But here you've got the methyl group in an equatorial position, which is going to be the lowest energy for this compound. When you have 2 substituents, then you have to start making choices. So let's say that you've got 2 methyl groups and they're both wedges. Well, you need to figure out if these are going to be equatorial or equatorial axial. And that's based on whether they're up or down. So here you've got your eye pointed toward the ring, And what you're asking yourself is whether these are up, up, or up, down. In this case, you have two up atoms, or up methyl groups, because they're both pointed toward you. Whereas if you have them trans, like in this example, then you're going to have both of them in equatorial positions while your protons are in axial positions. What you don't want to do is this one to the right, where you've got both of your methyl groups in axial positions. This one is a higher energy conformation, and it will exist for less of the time. Keep in mind that larger groups have preference for equatorial positions. So when you're looking at a molecule like this one, where you know that one of them must be equatorial and one of them must be axial, you have to pick which one is going into the axial and which one's going to the equatorial position. We know that the one on the left is wrong because this large tert-butyl group is occupying an axial position, which means it's undergoing 1,3 diaxial interactions with the tert-butyl group, which are larger than the 1,3 diaxial interactions that the methyl group is going to experience with a proton. Well, that's all I've got for chapter 4. Enjoy the next video.